Okay, so welcome to the beginning of last week already of complex analysis of this very intensive course, maybe, I think. It has been quite intensive for all of us. So we are going to do new things this week, some new things still, so it's not completely over yet. There are some important topics left to cover. Especially things like the automorphisms of a unit disk and such things is a very important topic. So we will get to this week, and then my plan is that probably the last lecture I will just try to impress you with some applications on the Riemann hypothesis or such things to tie everything together. But before that, we will cover some topics that are really important and part of the course. Okay. So one last effort. Now, so let me continue with these five types of integrals, right? Of real integrals. This thing due to alpha. I mean, the classification in quotes that he gives in his book. So we had type 5 left. So we covered all the types 1 to 4 last time. So now let's just quickly give you type 5. Give you an example of that, and then we move on. So type 5 is of the following kind. So it's an integral from, let's say, 0 to infinity of q of x log x dx, where q of x is a rational function. So it's equal to p of x over s of x, and we assume that degree of s is greater than or equal to degree of p plus 2, and we assume that it has no real poles, as usual. Okay, or at least in this case no poles on the real axis. Okay, but let's say no poles on R plus, okay, on the plus 2 real axis, this, including 0, okay? So we have this kind of integral, and if I want, I can also put some integer k here, okay? So Alphos actually just writes it like this. This fifth category is a little bit cryptic, to be honest. Like it's somehow supposed to be all the rest that he didn't cover in the first 4, and then he gives his logarithm as some kind of example. But so we will consider also, I mean, for k can certainly be larger than 1. But an integer, okay? I'm not going to give you square root of logarithm or something like that. So we can consider this, and I will jump directly to an example to show you this. So for example, let's compute. And I could choose just the basic one, but let's do it for k equals 2, okay? So let's do log squared x dx over x squared plus 1. And the funny thing about this is actually that when you compute log squared, the integral of log squared, then you will get the integral of log as a sort of for free. As a byproduct of your computation, you will get also the answer for k equals 1. Which is interesting. So let's do it for log squared. And I know I told you, I've mentioned this in previous courses, and I told you that normally you would consider, when you have a real function like this, you would just change x for z, and then you would try to find the suitable contour, right? But here you don't do that. So this is a little bit special for that reason. Okay, so the solution. Okay, so this is just a special trick for the logarithm, okay? So whenever you have a logarithm, you do this. So you consider, so you consider f of z is, for a suitable branch, you consider log to the power 3 of z over z squared plus 1, okay? For a suitable branch, and what is the suitable branch? Okay, so whenever you have these real integrals, and you want to integrate along 0 to infinity, so you want to integrate along this, 0 and out to infinity, okay? So when you do that, typically what you want to do is you want to take this keyhole contour, as we saw last time when we had the square roots here instead of log. You want to take this contour that goes around like this, okay? And then it goes around the big circle. So you want to do that. And usually, this is 99.9% of the case, that when you have a branch cut, you want to take the branch cut so that it coincides with the interval over which you integrate, okay? So that's why we did not take the principal branch of the square root, which would have been the negative axis, but we actually take away the part that we are interested in, and then we approach this part from above and below. And the fact that we didn't have the same value of the function here, because here it goes this way and here it goes that way, so if they had the same value in the limit here, they would just cancel out and we get absolutely nothing, okay? Everything would be 0. But because of a branch cut, we don't have the same value here as after we've gone a full lap around. They don't cancel out, but we leave some kind of remainder, okay? And this remainder will be something times the integral that we're interested in. And this is why we can actually compute this, otherwise it would just cancel if there were no branch cuts. And if we had taken the other branch cut, of course, we could not go all the way around because we could not pass this axis. So we have to take the branch cut, the thing that we're interested in. So here we will take the same branch cut. We will take this branch cut. So we define, so where log z is defined to be the real logarithm, okay, plus I argument of z, where the argument is in 0 to pi. So I take this branch cut, the green one here. Okay? And this is, of course, an analytic branch. And then consider this integral of f of z dz, where c is the keyhole contour. Okay. This is a word that you're allowed to use, by the way. I mean, if you want to solve something, especially if you have little time, like in an exam, you're allowed to write C as the keyhole contour and draw a sketch like this, and it's enough. We all agree we know what it means to be a keyhole contour. So you should be able to do it, of course, rigorously, but this is an important shorthand word you can use. So now everybody knows this is the contour I use. Small circle, big circle, and then these two lines. And it's assumed to be counterclockwise. So, okay, I have this part. But of course, in order to actually compute it, I will have to give names to these parts. So what did I use last time? I have already forgotten. I used CR, I think. CR for the big circle. So this is radius R, okay? And then you have this, then you have these segments here that goes from epsilon to R. Okay, this small circle here is the epsilon. And then you have this segment here that goes from R to epsilon. I write it like that, just to remember it goes from one direction to the other. And then, so the keyhole contour C is then equal to CR plus this R epsilon going in. Then you go around the small circle, and then you go along the epsilon R line, and then you've done the full path. So now this is something closed, and so we can integrate this thing here. So of course this thing is not 0 because this function f of z is not analytic inside where we integrate. Inside would be here, okay, away from this branch, because it has poles, of course, and the poles are going to be whenever z squared plus 1 is 0. So we're going to be here in I and minus I. Okay, these are the poles. So we have two poles. Sorry. So we have two poles. So poles. Okay, because of course the log cubed z does not contribute to these poles. Of course, in general, you have to check this, but in this case, it's really just when z squared plus 1 is 0. Okay, and so by the residue theorem, so sometimes, I mean, you do this residue theorem several times. You write down, okay, at this point, what do I get from a residue theorem? Just so you get a picture of what you need to estimate. Okay, so by the residue theorem, so what we get that this integral of c, f of z, z is equal to 2 pi I times the residues in I plus the residues in minus I of this f of z. Okay, and then we know that this is a sum of several parts, and some of them I'm interested in, and some of them I want to estimate the remaining. So, yeah, even for me, I don't have maybe a favorite order, but I think computing the residues is maybe the first step, because this you for sure have to always do. So let's compute the residues. So how would you do it? By the way, these poles, they are simple poles, right? Okay, because each pole is of order 1. So the residue here of f of z. So how do we want to compute it now? So we don't have so we have essentially two main ways that we compute residues, right? So, well, three main ways, let's say. So the first way would be to actually write down the power series expansion and then find the coefficient of 1 over z. But we're not going to do that. So this is rare that you do this. It's essentially if you have an essential singularity, you might do it. And it's not a rational function. Okay? So we're not going to do this. The residue is p of I over q prime of I in this case. So we're going to say that it's equal to the limit as z goes to I of z minus I f of z. Okay? And this is then equal to, so of course, this factors. So this is going to be equal to log I cubed over I plus I. Okay? So it's equal to this. So it's equal to 1 over 2I. And now what is log I to the cube? Okay. So how do we figure out what is log I to the cube? So it is equal to log, and I is now, so we have to always remember the branch that we chose. So we said that the arguments should be between 0 and 2 pi. So we have to be consistent. So I is equal to e to the I pi hat. Okay? And compute. So it's equal to 1 over 2I pi hat to the cube. Okay? And this is equal to, I'll just write down the answer in computation. So it's equal to minus pi cubed over 16. Okay? So this was the first one. In the same way, we see that the residue at minus I of f of z is equal to 27 pi cubed over 16. Okay? So if we sum these two things together and multiply by 2 pi I, then we get the value of this integral. Okay? So, okay, we don't do it yet. Could do it now if you want to. Okay, let's do it. So let's call this one, I don't know, let's not call it anything. So this implies that the integral of the f over this whole contour is equal to 2 pi I times minus this thing plus 27 pi cubed over 16. And this is, according to my notes, supposed to be equal to 13 pi to the power 4 over 16 No, over 4, sorry. Right, over 4 times I. Okay? So it's equal to this. Okay, so let's take this bottleneck. So we have this. Okay, so once you arrive at this point, you're fairly happy. Now you just have to check. So actually still, we haven't seen any reason why I considered log to the power 3 instead of log to the power 2. So of course, if you didn't know that this is going to work out, you might want to start in the other end to see that you actually get your integral somewhere that you're interested in. Because after doing all of this, it would be a total waste if I didn't know already before, because I've done these exercises before, that I will get somewhere. So this is the sum of 4 parts, and that actually I will get the integral I'm interested in, the real integral I'm interested in, will come out somewhere inside this. If it didn't, it was a total waste, what I just did. So indeed, if you didn't know this, you might have started with log squared, and then you would not have gotten the integral that you wanted. So now, step 2. Okay, so let's look at contribution from this integral over, let's say, so we had an integral over epsilon r, and we had an integral over r to epsilon of f of z dz. Okay? So this is where our integral is supposed to come from. And it doesn't matter that I don't do it in order, right? I just check what is the contribution from here. It is something, it's 7. Contribution from here is, 5. It doesn't matter, I don't do it in the order. So let's see. So on here, so to be able to do this, we consider that on this epsilon r, or when we come from above, let me just write it like this. So from above, so again now, when we approach the branch cut from above, okay, then we have log of this function, so log of z, log of r e to the I theta, or log of z, I don't know how to write this. I will write it and then you tell me if it's clear, and if it's not, then I will try to explain more. So log of z, it approaches log of x. So z is equal to x plus iy, and this tends to, if this tends to x, so I tends to 0, y tends to 0 from above, okay, this is what I want to say. So if this tends to 0 from above, then log z tends to log x. Okay? But let me write the other one and then we discuss if there is something unclear. So from below, so z is equal to x plus iy, and y tends to 0 from below. Okay? So we come from below now. Then we see that log z tends to log x plus something plus 2 pi r. So what I'm saying is just this thing which is, so here it's really the value of log x, but then when we go around, you're going to add, every lap you do with the log, you add the 2 pi r, okay? So when we come around here and approach the same line from the other direction, your value is no longer log x, or very close to log x, but it's very close to log x plus 2 pi r. So it means in the limit, you approach these things. So in the limit, okay, and so here really, I mean, you could write this down with the epsilons and the r's and the, arguments being 2 pi I minus some other epsilon, minus epsilon prime, and here being just epsilon prime, and you can write down all these things using epsilon and deltas if you want, okay? But really, let me just write it like this, that in the limit, this integral along these epsilon r plus r epsilon, okay, of f of z dz. So it tends to, as epsilon goes to 0 and r goes to plus infinity. So this is what I mean by in the limit. Okay? And epsilon going to 0 means I really approach this line, right? And r goes to infinity means I stretch out. So I'm not looking just at the finite interval here, but I'm looking at the whole thing. So this tends to integral from 0 to infinity, and I have to keep track of the orientation, right? So this one is in the correct order. This will go to 0, from 0 to infinity, but this will go from infinity to 0. So this is the same as saying that I go from minus, I can change this, and say I go from minus epsilon r, okay? So I integrate this other function. But, okay. If I write that, it will become weird. So this is, of course, this line is not the same as this line. Otherwise, if I write minus epsilon r, it looks like I'm taking the same thing minus the same thing, and I'm integrating over nothing. But this line was the one that was slightly above, and this was the line that was slightly below in my notation, okay? So they are really two different things. And this goes then to log cubed. So now take the contribution from the above part, okay? This one is counted positively, because I was going in the correct counterclockwise direction. So this is counted positively. So it's just, log z is just log x in the limit. So it's log x cubed. Okay, sorry, log x, let me write the cube here. Log x cubed. And the other one, from the below direction, then it goes in the other direction, so I would have to put with a minus. Okay? Minus log z, but now log z was approaching log x plus 2 pi r, and then to the cubed. Okay? So it's equal to all of this, the integral of that, dx. So this is what will appear in the limit. Yeah. Over x squared plus 1. Because x squared plus 1, nothing happens. This is a simple function. There are no branches here. So it just takes the same value. And we go around. Okay, so what happens, so if we look at what goes on when we just expand the parentheses here, so expand parentheses, so this is equal to the integral from 0 to infinity. Okay, so there's going to be, first of all, a contribution, so this is just going to be log x cubed. And here you will get log x cubed as the leading term as well. So you'll get log x cubed minus log x cubed. So you see, and this is okay because I didn't care about log x cubed. I wanted to compute log x squared, right? And this one will not cancel. You will get the log x squared times 2 pi I here. And this cancels against nothing. So you will get your integral. But note that if I had taken to consider from the beginning log x squared, then it would be squared here and it would cancel out. And I would not see the integral I wanted inside here. Okay? So this is why you take log x to the power plus 1, because the leading terms will cancel, and then you will get your integral. So let's see what happens. So this is equal to, let's see, where did I write it? So it's equal to 6 pi I. I'm sure I wrote it somewhere. I hope I'm not going to have to do this calculation again. Let's see. Okay. Yeah, so it's 6 pi I log squared x over x squared plus 1 dx. And then I will get plus, okay, so it's minus 6 pi I, sorry, minus 6 pi I log squared plus 12 pi squared integral of log x. So you see, you will get also a log x term, right? When you expand this parenthesis, you will get some log x. And then you will get another term with just the the constant ones, okay? So plus 8 pi cubed I integral 0 to infinity of 1 over x squared plus 1 dx. Okay, so you get all these kinds of terms from this. And the first terms with log cubed cancel. So now I have these three integrals. And now we look at what we have. And we note that this is the one I'm interested in, okay? So this is the one I want. Let's just call it I. And I want to solve later for I, right? So this is the one I want. This one, okay, so this one is something, but this is real, okay? So this is important to note, because you will see later. So now I have the contribution from integral of f over these two parts. I never did the big and the small circles, but the sum of what I have here plus the integral over the big and small circles should be equal to the full integral, which was equal to 13 pi to the 4 over 4 times I, which is purely imaginary number. So the fact that that this is real will mean that this is equal to 0. So we computed that as a byproduct. Okay? So we will see that. And this thing here, so this comes from arctangent, right? This is now just a real integral that we can compute. Okay? So this one is the arctangent. So by using the arctangent, we get that this is equal to what? Pi over 2, maybe? Yeah. Pi over 2. Okay, so we have to remember something from real analysis. Okay, so we get all these things. So, putting it together. Okay, so this integral over all of this thing. Yeah, okay, let me write it. So integral of c, f of c dz is equal to the integral of all this distance. It's equal to minus 6 pi I times the big I, the integral we're interested in. Okay, plus this real number, okay, plus 8 pi cubed over I times pi half. So 8 pi 4 I over 2. So 4 pi to 4I, maybe. Am I correct still? Okay. See better? So 4 pi 4 over I plus the integral along CR of f of z dz plus the integral along C epsilon of f of z dz. Okay. Actually, yeah. So the limit of this, of course. So integral along C. Yeah, I should. If I want to be really careful, I should write it like this. So of course there is this notion just of taking the limit. Here I wrote epsilon, so now I want to take the limit. I just say this minus the integral of C CR f of z dz minus the integral of C epsilon f of z dz. And to keep with my sloppy notation of tending towards, I have to write it like this. So it tends towards this minus 6 pi I plus the real number plus 4 pi 4 I. Okay? And it also tends to this business here. Okay? It also tends to this business. So this real thing we can completely ignore because in the limit it's equal to this. Okay, and also tends to 13 pi 4. Was it minus? 13 pi 4 over 4 I minus the limit as r goes to plus infinity, epsilon goes to 0 of these things, okay? Of these integrals of CR. Okay? So it's equal to this business. So what we have to do is estimate these integrals, okay? And then we will be able to conclude all this business, like this actually is real, this will have to be 0. So, how do you estimate this thing? Let me keep the bottom line here, because we'll use it. Okay, so estimate estimates. So the big circle. So when we look at the absolute value along this big circle, CR, so of f of g, dz. So now how can we estimate this? So we can do something similar to what we had last time. So we can say that this is equal to, so the integral along this CR circle. And I can multiply and I can divide by the same thing. This is not necessary again, but I can do it. I can say it's equal to this. Well, less than or equal to this. So the less than or equal comes just from the fact that I put the absolute value inside. Otherwise, I just multiply and divide it by z squared. And then I can say that this one, so this, of course, this is equal to r squared over r squared plus 1. Okay, so this one is bounded for r large. Okay, and then you have this thing here. This will go to 0. Okay, because log cubed of r e to the I theta here, if you look at its absolute value, okay, then it's equal to log cubed of r, and then, I mean, it's less than or equal to something like that, plus absolute value of I times something smaller. Sorry?
We can estimate 2 pi.
Yeah, so we can put, for example, 2 pi. So it's less than or equal to this plus 2 pi. So this thing here will go to 0 as r goes to plus infinity for these reasons. Okay, I'm writing everything a little bit quickly, but my goal is to explain to you what you have to understand. Okay? So this is the thing. So this thing will go to 0 as r goes to plus infinity. Okay? For the small circle, small circles are always a little bit more delicate. So in the other examples, like when we looked at type 3 or 2 or whatever it was, we used the Jordan's lemma, okay, on the big circle. And if you were to avoid, when you maybe had a pole around 0, you had to do this small bump, half circle around 0. And then for the small circle, you had to do something different. There's no Jordan lemma there. Jordan lemma is r goes to plus infinity. So in small circles, you need to be always a little bit more careful. So now this absolute value of f of z dz. So now how do we do that? So this is less than or equal to. So now let's see the following thing. So let me write here in color that z on this small circle will be, of course, of the form epsilon e to the I theta, where theta is between 0 and 2 pi. Okay? So it just means we can just write down explicitly. So log epsilon, log cubed epsilon, is equal to log epsilon plus I theta cubed. Okay. And so this absolute value is less than or equal to log epsilon plus 2 pi cubed. Okay, you can do that. And then I also, so this is the same estimate as before. And then I also have one other thing, and it's this thing here, z squared minus 1, I now want to deal with in some way. Okay, so, sorry, plus 1, yes. Plus 1, so this one is greater than or equal to, by the triangle inequality, 1 minus z squared. So this is a sort of very typical thing to need here, such an estimate. You can see why this is true. If you just put it on the other side, this is just the triangle inequality. So 1 is equal to z squared plus 1 minus z squared, and its absolute value is less than or equal to absolute value of z squared plus 1 plus absolute value of minus z squared, which is absolute value of z squared. Okay, so this means that that this thing here is less than or equal to, so now I have to put, so this log epsilon integral from 0 to infinity, and then I want to put it as log epsilon plus 2 pi cubed divided by absolute value of, so absolute value of z is epsilon. So 1 minus epsilon squared, and now absolute value of z. Why did I write 0 infinity? I mean, of course, this absolute value of z equal epsilon on this little circle. So it's less than or equal to this. Okay? And, okay, I don't need the absolute, no, I do need the absolute value, sorry. So it's equal to this. And now we, what do we do? So this is supposed to go to 0. Hang on, there's a pi epsilon coming in somewhere. Where is it?
Length.
Yes, it's the length, exactly. So we have a length. So now, by now we take the length. So, let me continue here. Just you can erase. So this is less than or equal to the maximum on this thing of this circle. Well, but this is already just a number. So this is less than or equal to 2 pi epsilon, right? Times whatever this is, absolute value of epsilon plus 2 pi to the cubed, like that, over 1 minus epsilon squared. So it's equal to this. And then, of course, you can take less than or equal to absolute value of log epsilon or whatever you want. And then you use this. Then you use that epsilon, log epsilon, as epsilon goes to 0. So what is this limit? So it is 0. Okay? So you see here you get epsilon log epsilon, and then you get 2 pi over this kind of thing, and then you get epsilon over this kind of thing, which is bounded. Okay? So, and epsilon over 1 minus epsilon squared is less than or equal to some small m as epsilon is small enough. Okay? Because this tends to 1 and this tends to 0. So its limit in 0 is small. Okay? So it's essentially equal to some constant. It's essentially equal to some constant, epsilon, log epsilon, and maybe to some power, okay, plus some other constant. Yeah. So I don't want to write down. I mean, I'm happy to see that it works. Then you know how you would write out these parentheses how you would do it all. But you see every term will go to 0. Okay, so this thing goes to 0 as epsilon goes to 0. Okay. Check for details. I write it like that. Okay? Because I don't want to spend the entire lecture on this estimate. So now let's just sum up. So to sum up, these two things, the contribution of this tends to 0. So really this thing here is the limit is equal to this minus 13 pi f. So minus 6 pi I times this integral that we wanted. So let me write it out then for once. Plus 12 pi squared log x square plus 1 plus 4 pi 4i. Is this 4 pi 4i correct by the way? Yes, it is. Okay, is equal to minus 13 pi 4 over 4 I. Okay, this is purely imaginary. This is a common trick, by the way. This is real. Okay, so this means that, so now the thing I said earlier, this really implies that this is equal to 0. Okay, and it implies also that this integral we wanted, log squared x over x squared plus 1 dx is equal to, you just solve this out and you get that it's equal to pi cubed over a. Okay, check. So of course from this, you forget about that. This times this plus this is equal to this. You just get the this. Okay? Yeah, so the trickiest part, as always, is to try and estimate these integrals. I mean, in principle, that's where you might need to think a little bit, or click around, do some tricks. But, you know, yeah, so now we have seen 5 types of integrals. By far, not every integral is of this type. I mean, you can also imagine other integrals, for sure. But if you know these 5 types, you've already come a far way. And these are very standardized, you know, it's almost algorithmic, of course, like how you do these. You always choose the same contour, you always just calculate the residues, and then you do some small variant of some trick to try to see that the integrals tend to something. In this case, usually 0, but it could be something else. But, you know, it's also then the next level after that is to be a little bit free, you know, in your abilities, that you can choose maybe a different contour or adapt to some slightly trickier or different situations, so, which is also necessary. So when I write these things, I know I'm not doing it super well. I mean, actually, if I corrected it myself, I would probably not be super happy. But this is to explain to you what's going on, right? And then you have to interpret it. Okay, how do I write it nicely? I understood what's going on. Now, you know, do the appropriate details to show this. And I'm more seeing this as trying to give you some hint rather than saying exactly how you write out all the details. Yeah. On the other hand, when you do it, give the necessary details, but don't do too much, because, you know, on the exam, if there is, you already know there will be one integral on the exam, right? And this exam, for sure, somewhere there will be an integral. And if you spend 2 hours with this integral, it's not good. Okay. So you have to learn to do this in half an hour, which is possible. It takes about half an hour probably to write such a thing. But you can do it in something like half an hour. Okay? If you write the appropriate kind of amount of detail. So let me just give this final remark for the moment. There are other integrals too. Okay, so some of them actually you can, by a change of variable, bring to one of the 5 types. This is one approach. If you see something and you say, I can take this change of variable, it's one of my 5 types, and then I already know exactly what to do because I studied them. So you can do that. That's perfectly fine. Then you have others where maybe it's not too obvious if you want to do that, or maybe you just don't want to. So you can look at, I want to show this also for other pedagogical reasons. You can do something like this. Such an integral where alpha is what? So alpha, there was a condition on alpha and beta I had. So absolute value of alpha is less than 1, and a is greater than 1. It's a real number. Okay. But alpha is complex. No, alpha is not complex. Alpha is also real, for sure. That's true. So alpha also real, and a real. Okay, let me write it like that. So if you have such an integral, then actually it's nice. So you see here the integral is from 0 to 1, and then you have some kind of quotient here, which is actually a Möbius transform to the power alpha, and then you divide by some other thing, 1 over x minus 2 or something. Okay? So this is nice for the reason that, okay, it incorporates everything. So this is the kind of questions that you like when you teach a course, when to test the student. Because here you could use Möbius transforms to compute an integral with the residue theorem. It has everything. So really here, and it gives me the opportunity to just mention briefly branch cuts again. So here, this thing here, where is it defined? Where should I take the branch cut? And a hint is this fact that I told you in the beginning, that we have the integral from 0 to 1. Okay, and it's not not a random thing. It's not a coincidence. Because actually, if you take this line here, so here is 0, and here is 1. So if you take away that, then actually I claim it is defined on this. But okay, if you don't see that, how would you go about it? You say, okay, they gave me the integral from 0 to 1. Then it means that usually I should take the branch cut on the interval that I want to integrate. In this case, so let me write down 0 to 1. And let's imagine I wanted to take this as a branch cut, and then I would probably want to take a contour that I would like to have a line going very close below. Because it's a power, I would like to have a line going very close above. And then I would like to make it closed, somehow. So the natural thing, I can do anything, right? But in one way or another, I will do something like take a small circle around, go here, take a small circle around, and do that. So I'm not going to compute the entire integral now, but I just want to show you that you can have also contours like this. So, it's important to know the 5 types, but don't be completely rigidly stuck in your mind on this being the only possibility. So, you can have, for example, this. And so when you see this, you imagine, maybe this is something like this I want to do. But still you should check, is this really well defined? So you want to consider f of z is z, z over 1 minus z times 1 over z minus a, okay, just the power alpha, times 1 over z minus a. You want to consider this function. Is this well defined on, so is this analytic and single valued on C taking away this 0, 1? So I think this is a good question. Not even just to test you if you can apply the residue theorem, but just in general to see, have you understood, where functions are analytic and single valued with an appropriate branch cut or not? Because actually this turns out to be yes. But how can you see it? So you have a power, okay, So this is the function, so this is a power function. So this is t to the power alpha, where t is equal to z over 1 minus z. Okay? Now we know that this is defined if we remove an entire axis going out to infinity. So then we just have to see what does this do between 0 and 1. So what we do is we understand this Möbius transform. So the Möbius transform, it takes this line. So let me draw another picture, okay? So this is still 0 and 1. So it takes this thing, okay? And it maps it so what is the image of this line under the Möbius transform? Or of this segment under the Möbius transform? Circle, line, what? Real line? Positive real line, exactly. So it's a positive real line. So this thing is mapped onto this, the entire positive real line. Okay? So here it says 1, so it stops. Here it goes out to infinity. Okay? As shown by the fact that I can go around. Okay? So this is, 1 is now here, this goes out to infinity. So this one is mapped to here. And then in order to define such a power, such a function, I can do it with really what is the way to define powers in complex analysis? If I give you b to the power a in complex analysis, even in real analysis, you remember b to the power a is equal to e to the a log b, and if log b is analytic and single valued, then this is analytic and single valued. Okay? So really what we see is that since this maps the branch onto something, and this is a well-defined branch of log, okay, so since log w has a well-defined single-valued branch on C minus this, this implies that log of z over 1 minus z has the same thing, is analytic and single valued on C minus this line. Because everything that's outside here maps to what's outside here, and that's all I needed. Okay? So this is what you had to check. And then you have this remaining part, 1 over z minus a. Okay? But this, because a is greater than 1, this will not disturb us, as you can check. Okay? So then you check this is actually well defined. And so of course the first thing when you compute the integral is define, you consider such a function and you define the power. Okay? So then you define the power using this kind of branch. Okay? So this to the power alpha is e to the alpha log of this branch, z over 1 minus z, where the argument is then between 0 and 2 pi. Okay?
So,
yes?
So in general, if we have S composed with G, where G is analytic, so we can say that a branch cut of S composed with G is the inverse image of a branch cut of S by G. So
now you lost me. What? Okay, so many words. Okay,
yeah,
inverse.
So
Yeah.
S composed with G.
Yeah.
Where G is analytic. So a branch cut for F composed with G.
Yeah.
So what we do, we choose a branch cut for F, and we take its inverse image by G.
Branch cut for F.
Yes.
We take G inverse.
Minus 1 of this branch cut of F. So this gives us the branch cut of F composed with G, right? In general.
Yeah, this is very confusing, but maybe let us check it afterwards, okay? Yeah, when we can write it down properly. No, okay. Yeah, but you do have another remark, but in a similar spirit, is you have this. You should remember this exercise that I gave you about log of f of z, that you can define an analytic branch if f has no zeros, inside your domain. So you should remember that. Okay. Anyway, this was just to show you that you can have this kind of stuff, I will perhaps solve this one before the end of the week at some point. But now I want to move on. Okay, so now what I want to talk about is local properties of holomorphic functions. So now we leave behind completely this residue theorem. Okay? And now we try to understand, so we have three important theorems that I absolutely have to tell you about, because anything else would be a sin in complex analysis course. So it's the open mapping theorem, it's the maximum principle, and it's Schwartz lemma. Okay? So there is no choice. This is something that has to be covered, for sure. It's an important topic. And it's about local behavior of analytic functions. Okay, so now we have spent a week or a week and a half, 2 weeks, discussing meromorphic functions. There were poles, there were essential singularities, and so on. Now we are back to the world of analytic functions, okay? So no more dividing by x squared plus 1, and now we consider the analytic functions for a while, and try to understand more, in a more fine way, what they look like locally around the point. Okay, so this is about more special properties of analytic functions, basically, this chapter. So, for example, z goes to z squared. Okay, it sends, first of all, it sends the half disk here, it sends this into the full disk minus this. Okay, so z goes to z squared. So we have this kind of thing, and the picture is that, so z goes to w, which I define as z squared, and then we can see that for any w not 0, there are exactly 2 pre-images under this map. Okay? Because you could have taken, of course, you could have taken something here, but you could also have taken something on the other white side here. And another way of saying this, which I like better, so there are many ways of saying this actually. There are 2 pre-images, or there are zeros of multiplicity 2. Or my favorite way of saying this, and somehow conceptually maybe the most important and most commonly seen in mathematics, is that the image of a circle around 0, or the image of a small neighborhood. So remember, local behavior. So everything now is about small neighborhoods around points. And if they are too big, so they give us trouble, we just shrink it. Okay, everything is local. So the image of a small neighborhood around 0 covers a local neighborhood of 0 n times. In this case, n equals 2. But if you take z to zn, so z to zn, and then you take the unit disk. So then you see that, so this is f of z. So then we see that f of d, we say that it covers d. So d is now inside, covers d n times. Okay, what do I mean? I mean, if I take the unit circle, so this is 1, and I have elements here. They are of the form r e to the I theta, where r is between 0 and 1. This is close. R is between 0 and 1, and theta is between 0 and 2 pi. Then this z to zn, what is the image? N is a positive integer. Well, the image is this circle, exactly the same, But the image is, of course, Rn e to the I n theta. So if we were to run one lap around here and consider the images of all these possible things, then as I go one lap around here, I will go n laps around here. Okay? So I'll make some kind of spiral. So actually the image of this, okay, in a set theoretical sense, the image is just the unit disk. But in another sense, which we want to keep track of in complex analysis, it's actually in some sense a stack of n disks, one on top of each other. So we say that it covers the disk n times, because it goes around n times. Now this is what later, if you study complex geometry or other branches of mathematics, you have this thing called the branched covering, for example, or these covering spaces, which essentially means that above one point you have n points. Okay? So you have all these kind of mathematical objects that are very important, that you will see much more of as you go on and become even more advanced. Okay? So this is a very common prototype of this. That you have n copies of the disk. It covers it 10 times. Does this make some sense, what I say? In set theoretical sense, it's just the unit disk, but in a stronger sense, we actually go around n times here. So it's covered n times. Okay? So, question?
In set theoretical sense, the pre-images are exactly n.
Yeah. So in this sense, we can still say that the pre-images are n. But if I look at the image is still the unit disk in a set theoretical sense. Yeah, and of course, I can also say this in a different way. I can say that f of z minus w, okay, has two zeros in this case, or n zeros in this case, counted with multiplicity. So if I say this counted with multiplicity phrase, I can remove this. I no longer have to say w not equal to 0. Because the pre-image of, 0 is sent to 0, but this equation f of z minus 0, the equation, this has two roots. So if I look at the zeros of z squared, in this case, then it has, the zeros are 0, but I told you this thing about multiplicity, so the zeros are 0 and 0. So it's with multiplicity too. So they have two zeros counted with multiplicity. So this is a nice way to say these things. Okay, and then we can note that in general, so if f of g has a 0, so analytic, of course, so analytic has a 0 of order n at some point, z0, then f of z is locally written in this favorite way of everyone, like this, where g is analytic and g of z0 is not 0. Okay, so we have this. So in some sense, it looks a little bit like this prototypical example. Okay? So, this is now just some kind of introduction, so I will tell you rigorously where this comes in later. We'll revisit it. But it looks a little bit like this power n function, which yields this n-fold covering, but then times something analytic. But this will actually turn out to be a nice function. Because g of z0 is not 0, it means that you can define a branch of a logarithm in a neighborhood of this. This was the exercise, remember? If f of z has no zeros, you can define an analytic branch of log of f. You can define an analytic branch of log of g, okay? And if you can define an analytic branch of log of g, you can define an analytic branch of any square roots or cube roots and so on, right? E to the 1 over n log g of z. So you can write this, you can define nth square root of this, and you can write this as z minus z0 times the nth square root to the power n. And then you get that this is something, however this behaves on the inside, to the power n. And you will get this similar behavior. Okay? I said it in words, I will put everything in writing, okay, in the next half hour, so don't worry. So let's have this proposition. So the question is the following. Let me write the question after all. So the question is, so if f of z so equals w has n solutions with multiplicity, then it's the same true for f of z equals something else, another letter, equals u for u, let's just put it like that, for u almost equal to w. So if u is very close to w, can we still find n solutions to the equation f of z equals u? So you take the neighborhood of w, you say that n solutions here, so for every other u in this neighborhood, can we still find n solutions of this equation? And the answer is actually yes. The answer is yes. We have a following proposition. So suppose that f is analytic at z0, and suppose that f of z0, so this is the notation I will use, okay? So z0 is mapped to w0. And this, so with multiplicity n, so that means that f of z minus w0 has a 0 of order n in z0. Okay, so we multiplicity n. So this means, okay, let me write it. F of z minus w0 has a 0 of order n in z equals z0. It was already erased. Then, for every epsilon sufficiently small, there exists a delta such that if A is in this disk of W0, so in the neighborhood of radius delta of W0, then also f of z minus A has a 0 of order n. Sorry. This has n zeros inside the first disk around z0 with radius epsilon. Okay, so this is very tricky proposition, I think. You can look at this and you don't really understand what it says. I mean, it's not very tricky, but when you read it, it doesn't really speak to you very much. So let's just say, what does it say? So first of all, in particular, it means that a neighborhood, is this fine for you? MTH is neighborhood. So a neighborhood of f of z0 in the image, okay? So a neighborhood of f of z0 is contained in the image of the neighborhood of z0. Just write it like that. Which is in particular inside f of any open set. Okay? So let's say that z0 is in some open set omega, and then this is inside f of omega. picture, need still a picture. F is defined in omega, okay, inside C. You have Z0, you take a small neighborhood of radius epsilon, and you take it so small so that it's still inside omega, which is possible because omega is open. Okay? Then you map this thing using F, and the image F of omega is something, it looks like this. This is F of omega. Okay? And this disk is mapped to something. And what I say here is that the neighborhood, so first of all we have F of Z0 somewhere. And then we have this disk of radius delta. So F of Z0 is W0, right? Okay, so we have this neighborhood. And now this neighborhood is contained inside the image of this neighborhood. This is what it says. And in particular, actually, so the most important consequence, but much weaker than what we need. I mean, this weaker consequence is that this neighborhood is contained inside the image of this neighborhood. But what it says is even stronger, that for any point inside this neighborhood, you have n pre-images. This is what it says, okay? So not only Z0, F of Z0 has n pre-images, but any other point in this disk has n pre-images in this disk. But in particular, the image of the small disk here is inside F of omega. Yeah, so this disk, you can find a disk here, which is inside F of omega. Okay, I know this is sort of hard to, it's a little bit hard to grasp, maybe, but I assure you it is very possible if you just look at it again. Okay, let's see. So the corollary, let me tell you just, in case you're doubting, you think that seems completely useless, in case you're wondering, let me just tell you the corollary that we want to get to. The first corollary we want to get to, one in many steps of things, is that it maps, an analytic map maps open sets to open sets. Okay? This is going to be a consequence of this lemma, or of this proposition. Because, okay, you can choose such an epsilon, such as this disk is inside. And then showing that if omega is open, then this image F of omega is open, means that you can find the neighborhood around F of Z0, which is still inside F of omega. And this is what I'm trying to say, that if you decipher this, if you interpret correctly this proposition, this is a consequence. Okay? And that's the famous open mapping theorem. And the open mapping theorem follows immediately from this proposition, which is something stronger. Okay? So now let's try to prove it. So what I want to prove, again, let's remind ourselves, is that we want to study the pre-images of the function f of z minus a for some other a inside this disk. Okay, we want to show that there's some small close to. Okay, let's talking. Let's get on with the proof. So since zeros of f are isolated, this we know, okay? This we saw in some other class. Then without loss of generality, we can assume that epsilon is so small that z0 is the only root. So assume that z0 is the only root of f of z minus w0 in this disk of radius epsilon around Z0. Okay, so if I look at, so W is equal to f of Z0 by definition, okay? So you look at f of Z0, you can take some small disk such that f of z minus, well, actually, you can take a small disk around Z0 such that this is the only solution of this equation. Because if it had another one, it would have to be here, since the zeros are isolated, and I can just take this disk small enough so that it contains only one. Okay, so this is just the prefix. Now consider, so this is the key. So consider the following quantities. So we want to study zeros of this function, or zeros of f of z minus a for some other a inside here. Okay? So what are the zeros of f of z minus w0, and what are the zeros of f of the number of zeros of f of z minus a? And now we have an application of something that we saw. Sorry? Identity theorem. No, actually. No. Rouchet or argument principle. Exactly. Argument principle. So the argument principle says that you can compute this integral of f prime over f. Okay? And then this is 2 pi I times the number of zeros minus the number of poles. Up to the winding number, okay? But now, first of all, it's analytic, so it has no poles. So it's equal to 2 pi I times the number of zeros up to the winding number, okay? So if we take the winding number to be always 1, inside gamma, then so something that winds around only once, then we get actually exactly the number of zeros from the argument principle. So what we want to consider is the following function. I call it z of a, not because of my name, but because zeros, yes? So z of a, let's define it to be 1 over 2 pi I integral along this small circle of radius epsilon around Z0. And what function should I integrate actually? So I'm interested in the number of zeros of this g of z. So I should take g prime of z over g of z. But g prime is f prime, because a is a constant. But g of z is f of z minus a. And then I take gz. So this is my function, and I claim that this now measures the number of zeros because this winds around once. So this is now equal to the number of zeros of f of z minus a inside a very small circle, because we're up to local properties now, inside the small circle around z0 of radius epsilon. Okay? So this is an important thing. But, so what we want is to show that z of a is equal to z of w0, which by definition is equal to n. Okay?
Z of z0.
Sorry? No, so a is in the image here, actually. So you see, so f of z minus, so w0. Yeah. So a here is in the image of omega, if you want, okay? F of omega, if everything is defined on omega. Is this clear? So this is what we want to show. We want to show that there is such a small disk, so in some small neighborhood, a minus w0 less than delta. This is what we want to show. That there is such a neighborhood with w0, such that for every other point in this small neighborhood, the number of zeros of f of z minus a is the same as the number of zeros for f of z minus w0, the center of this disk, which is then n, because I assumed in my hypothesis that f of z minus w0 has a 0 for the n. Okay? And I assumed there was only one zero inside. And I could do that without loss of generality. So this is what we want to show. But this is actually, with everything that we know and everything we have seen in this course, this is actually something fairly immediate. So let's see if you can see how you can show this. So there are sort of two ideas. So one idea would be that if we could understand the image of this disk under F, or this, so this is actually a circle, right? So if we could understand that this circle of radius epsilon, that it was mapped to something that, so this is Z0, and then this is F of Z0. So is this mapped to something that winds around precisely once? Does this have the same winding number? If it did, if we knew that, then we could actually finish immediately, okay, with this business. But we don't really know how to justify this yet. So therefore I want to give, at this moment, a simpler argument based on continuity. So give an argument based on continuity. And the argument is as follows, that this function z of a is the number of zeros of some function. So this function only takes integer values. Okay? So if we could show that this argument is that this z of a is continuous in some small disk, okay, then it would have to be constant. And in this disk it would have to be equal to, in particular, z of w0, because w0 is in this small disk. So if we could show that this function a goes to z of a is continuous, so in a neighborhood of w0, okay, then it is constant there. Because z of a is always an integer. Okay. Well, in fact, it's a positive integer. Okay. So, how do we show this? To see this, we have an epsilon. Take some epsilon. And take delta to be the minimum absolute value on the circle around z0 of this function f of z minus w0. Okay, let delta be this minimum. Now let's do this here. Okay, so then just let's try to interpret this. So now, A being a point in this neighborhood of W0 in the image, what does it mean if delta is this now? So let A be such a point. So then f of z minus W0 has to be greater than or equal to delta. Okay, and that means, so on this, by definition. Okay, and this means that 1 over f of z minus W0 is less than or equal to 1 over delta. Okay, again on this circle. So we wanted, of course, we want to estimate this such an integral, right? And so we look at the part that gives us trouble here, and this one is less than or equal to its absolute value is bounded by 1 over delta from above. So this means that if we look at this z of a minus z of w0, then this is less than or equal to 1 over delta, so let me write delta to the power minus 1 over 2 pi I, integral along this equal to epsilon of f prime of z. So what do I have actually? So I wanted to take z of a minus z of w0. So it means, yeah, so for every point, yeah, it satisfies this. So I have f prime of z times 1 over f of z minus a over 1 minus, yeah, so I have some constant here, I guess. I have some constant. Times absolute value of f prime of z dz. Okay? I don't have to, so again, I'm not making explicit all the constants because it's a headache. I mean, at least, you know what they say, in mathematics, there are several stages. There's the stage where you don't know how to do anything rigorously, then that's the stage where, you learn how to do things rigorously, and it's very important every detail, which is usually somewhere in masters. And then there's the step where you go beyond that and you just say, I know how to do this rigorously, but I understand it deeply, so I don't need to do it. I see that, I know, everybody knows what we mean. We could do it rigorously if we wanted to. This is the research step, when you have internalized everything. So this is clear. I don't have to give more steps. And now, what does this mean? This means, so this kind of thing, when epsilon goes to 0, so this is less than or equal to what I want to show. I want to show that this is less than or equal to some constant again, c tilde times epsilon. And indeed it's clear that it is. Okay. So again you can write it up. So you see that if a goes to w0, then this thing goes to 0. This is what you need to show. So a tends towards w0 implies that z of a goes to z of w0. So it's continuous. Okay? No? Not really.
At Z0.
Sorry?
We have shown the continuity at Z0.
No. Why? What?
At W0, I mean.
Yes. You're right. Okay. Yeah, you mean I was taking epsilon here? To be, yeah, you're right. Okay. Anyway, this is continuous, this function. I'll leave it as an exercise in case I messed it up. So we'll discuss it, afterwards. Let me just write down the corollary and then we'll discuss it. Okay. So corollary, open mapping theorem. I will just finish by this. This is the corollary. So suppose f is analytic and non-constant, then f takes open sets to open sets. Okay, this is the open mapping theorem. Okay, time is up, so I'll stop.